Well, thanks very much, Leonid, and actually to all the organizers for inviting me to this very nice conference in this wonderful location. Um, yes, and actually thank you everyone for making it in after the reception. I was kind of wondering how many people would be here, but good for you. And anyway, so yes, so I'm actually going to be telling you about basically 10 years of effort in looking at this class of 4 and 5D double perovskites. And because it's a 10-year 10-year review, there's actually many collaborators that I've had over that time. Let's see, yeah, good. And so this group, so these are the collaborators. Some of them are older, some of them are recent, but it's basically my group at McMaster University in Canada with a very strong collaboration with a U of Toronto theory group of Aaron Paramakanti. And so the people that you see here, they're a mixture of synthesis people, theorists, and neutron scatterers, and that's why there's, relatively speaking, a large number of collaborators. So I'm going to be talking about double perovskites, and well, today is Double Perovskite Day here at this meeting. So I think you probably already know what a double perovskite is, but this is a perovskite, right? So perovskites are very common in nature, especially in transition metal oxides, and so you have this transition metal O6 sort of architectural motif, and then you build the crystal up around it. And of course, for double perovskites, you have the same sort of structure, but now you alternate every second transition metal oxygen octahedron with a different transition metal. And so you've got two transition metals here, so there's many perovskites, so it won't surprise you that there's many double perovskites, hundreds of them actually, and so you can have you have these two transition metal sites, and in all the cases I'll be showing you, one of them has a partially filled D shell and the other one doesn't. Okay, so one of them, if you like, is magnetic and the other one isn't. But it doesn't have to be that way. There's lots that are mixed both ways, and there's metals and insulators and so forth. Anyway, these are the ones that I'm going to talk about here that we made up, and we'll basically be running through this systematically just changing the number of d electrons that we're dealing with on the B site here. And so we can have either a single electron, 2 electrons, or 3 electrons. And we do this simply by varying the valence state of the 5D state. And actually the valence state, so osmium and rhenium and these sorts of ions actually have a lot of flexibility, and that's one of the reasons why this is a very useful playground. Now, as I said, there are very many double perovskites. So if you want to study double perovskites, you're going to have to find some selection criteria to select down, because you're not going to study everything. And anyway, so our selection criteria has been those double perovskites that remain cubic down to low temperatures. Of course, when we start the project, we don't know that, right? But that's what we're trying to aim for. And the reason for that is because if you just look at, let's say, the B or the B prime site, and they're cubic, then those sites form a network of edge-sharing tetrahedra, and the whole field of geometrical frustration is kind of based on architectures that involve either edge or corner-sharing triangles or tetrahedra. So we were interested in geometrical frustration, and so that's why we selected or tried to select these. And actually, the ones that I'll show here, the 4 at the bottom, the D2s and D3s, well, all of them are cubic at room temperature, but the D2s and D3s stay cubic down to low temperatures. The D1 doesn't. Actually, there'll be a lot of talk about this particular D1 later today, the next talk, for example, but there's about 4 talks on it. And so we'll see it's quite interesting. And so actually, the cubic structure is unusual, right? It's the exception. It's not the rule. The rule is something more like this, so that you have some monoclinic distortion or orthorhombic distortion, where there's basically a tilting of the transition metal octahedras. So that's what we're trying to avoid, actually, for the most part. Okay, and see. Yes, so the periodic table is our playground, and over 10 years, these are the different ions that we've been trying to put on both the B site and the B prime site. And in all these cases, as I said, the B site has a filled D levels, and these are the various elements that we put into the B prime site that have partially filled 4 and 5D levels. And of course, you've got spin orbit coupling if these are, well, even if they're metals, but if these are all insulators. And so that's increasing like Z squared. So you can imagine doing studies where you can have the same electron count, but have it in a 4D and 5D scenario. And you can sort of imagine that all you're doing is tuning the spin orbit coupling, which of course isn't correct. But it's not a bad way of thinking about it to start. Anyway, so these by themselves actually would give you 42 different double perovskites if they were all stable. They're not all stable, okay, but nonetheless, this is where we are playing around. And of course, this is the standard single ion, one electron picture that you get for the D levels, in the the transition metal 06 octahedra, and that is you get the Eg T2G splitting by the octahedral crystal field, and then if you apply spin orbit coupling, you'll split the 6 levels in the T2G into a low energy quartet that has a J effective of 3 halves and a high energy doublet. So this was gone through in a lot of details on Monday, and yeah, so I'm going to assume that you remember that. And anyway, and so now we're just going to basically occupy these levels, and I'm going to go through it in kind of the order that we went through it, although I'm going to make it sound like we were more systematic and organized than we actually were. But nonetheless, this is the way we thought about it. And so to begin with, I'm going to talk about our work on D3s, 4D3s and 5D3s. And then, of course, you've got 3 electrons in the D shell that if you got all the way to this point in the phase diagram, you would partially fill the quartet here. But actually, even without the spin orbit coupling, if you just take a step back, and you would have 3 electrons that would give you a half-filled T2G shell. And so long as the Hund's coupling was actually stronger than the spin orbit coupling, then that would leave you with an orbital singlet, and there would be no orbital angular momentum in this very simple picture. So this picture is not correct, but nonetheless, that is how we were thinking of it at the time. And we were imagining that these systems would be, essentially very good realizations of Heisenberg magnetism, on an FCC lattice. That's why we were trying to study them first. And we also had expectations for what would happen in that case. And one of the expectations, so we would expect magnetic dipole order for the spin moments, pretty big spin moments because you've got 3 electrons, and nice spin waves with Goldstone modes. So we had well-defined expectations for what we were going to find, and a lot of those actually were realized. And so I'm showing you work now on barium-2 yttrium osmate, which is 5D3. And indeed, when you get below about 70 Kelvin, so this is powder neutron diffraction measurements. And this is the growth of the Bragg peaks due to the dipole order. The dipole order is easy to observe because it's a big ordered moment. The big ordered moment is 1.6 mu b, so it's not 3 mu b, which you would get, if everything ordered, but it's about half that. And it has a type 1 antiferromagnetic structure, which I'm drawing here, which actually is not correct, but that is the way we were thinking about it. And it's so this I would describe as a single K antiferromagnetic structure. So you've got ferromagnetic sheets of moments, and they're stacked antiferromagnetically along one direction. So it's just a very simple way of representing, one of the possible magnetically ordered states, which would give rise to these sorts of Bragg peaks. Okay, so actually this was not a surprise. That's more or less what we expected, although we were disappointed that the ordering temperature was as high as it was because we were interested in geometrical frustration. But then the surprise came when we looked at the inelastic scattering in the same samples. And so this is time of flight inelastic scattering from this system. And so this is energy versus mod Q. And so if you look at where the Bragg peaks are, so you look at the wave vectors where the Bragg peaks are, and just above them in energy, you can see that there's a clearly gapped excitation, and it's got a big gap, okay? And so the big gap is at about 17 millielectron volts, which was really a surprise, because we expected to have no orbital angular momentum, and so that was a bit of a surprise. And in fact, we did a comparative study. So we looked at both the 5D3 system that's based on osmium and the 4D3 system that's based on ruthenium. So ruthenium is just above osmium in the periodic table. And we were sort of imagining that we'd have the same physics, but we'd be tuning the spin-orbit coupling. And that's almost correct, actually. There are actually subtle differences, but I'm not going to go into them. But in both cases, you had what appeared to be a simple antiferromagnetic structure with a large moment, pretty large moment, and these gapped excitation spectrum at low temperatures. So with a gap of about 17 MeV for the osmate and about 5 MeV for the ruthenate. So the ratio of the gaps, 3 to 1, is about the ratio of what we naively think of as the spin-orbit coupling strength, right? So if you just take the Z and you take the square of that, then that also gives you a ratio of about 3. And anyway, so it does seem to be going with the spin-orbit coupling, which perhaps is not surprising. And in due course, and by due course I mean like about 5 or 6 years later, we got together with Leonid, and he told us what was going on, and so this was great. So actually, we got together while I was on sabbatical in Paris, and Leonid was at Collège de France, and Antoine Georges was the boson that linked us. Anyway, so this was all very good, and so in fact, so this resulted in a publication for Leonid just last year. And basically, he was putting, I can't do justice to what he's done in this paper, but he was putting the spin-orbit coupling, back into the problem through, higher order perturbation that is, a more sophisticated version than the version that I told you about. So I'm not going to go into any of that. But the net result is that there are both dipole and octopole moments on the osmium site. So, and this is the predicted structure, which is actually a 2K structure, not a 1K structure that I was showing you before. You've got the magnetic dipole moments in purple on the osmium site and the octupolar moments in orange. I think that's the code. At any rate, this 2K structure, it's a coherent superposition of two 1K structures. And of course, you can also get 3K structures as well. And it turns out that multi-domains of a 1K antiferromagnetic structure and a 2K antiferromagnetic structure and a 3K antiferromagnetic structure, they all give you exactly the same sequence of Bragg peaks and intensities. So this is referred to as the phase problem in crystallography. We can't tell them apart. But most importantly, he was able to calculate the spin excitation spectrum, and indeed, he could get very good semi-quantitative agreement, actually essentially account for the gap and the ratio of the gap between these systems. So actually, this anomaly was well explained by the theory. So now I'm going to remove an electron and go to the 5D2 cases. So now there clearly is orbital angular momentum, no matter how you think about it. And so this is the case that was discussed by Aaron Paramokanti on Monday. And so we've got two electrons that are occupying the Jz equals 1/2 and Jz equals 3/2 states here. And if you combine those two, you'll get a J equals 2 degree of freedom. And so there's 2J plus 1, so a 5-fold degeneracy associated with this. So it's a lot like the normal d electron type physics. And so this is actually realized in this family of double perovskites. So they're still osmates, but we're moving them down to 5d2 by controlling the valence of the B site. Okay? So these are all 5d2s. I'll show you data on this in a minute, but they all stay cubic from room temperature to low temperatures, and we have very high tolerance on that. And so this is what the heat capacity looks like, and there's clearly some sort of a phase transition at about 50 Kelvin or so. And then below 50 Kelvin, this is MUSR data that was measured by my colleague at McMaster, Graham Luke. And so you see oscillations in the zero longitudinal field, MUSR, so clearly there's some magnetic field there. And so, we were pretty much convinced that this is some sort of magnetic long-range order, and it's just a matter of, solving the crystallographic problem. But there were some oddities associated with this as well. And so, the first of the oddities came from trying to account for the entropy in this system. And so to do that, you've basically got to integrate up the magnetic heat capacity divided by T as a function of temperature to get the entropy. And that's relatively straightforward to do. You see it done all the time. The only thing I'd like to point out here is that it's not a trivial thing to do when the phase transition of interest is anything above 10 Kelvin. And the reason for that is because the heat capacity is completely dominated by the phonons. So what we typically do is we try to synthesize a magnetic blank, so something that is otherwise the same as the material you're interested in, but it has no d electrons. And so in this case, it's actually this barium-2 magnesium tungstate, which has an empty 5D shell. But the phonons and such should be almost identical. So then you can do a pretty good subtraction of the two and isolate the magnetic component. Anyway, if you do that, you discover that you've got an impurity phase. That's one thing. But you can also isolate the entropy. And the entropy is actually pretty low. Okay? And I'll talk about exactly how low it is. We're actually recovering about R log 2 in entropy if we go up to twice the ordering temperature. And that's not R log 5, which is what you would expect if you have just a J equals 2 degree of freedom. So, right. So, and actually, that's true throughout this entire family. So now I'm showing you these types of measurements on 2 of these samples. There's some variation. You can see there's some variation in accounting for the entropy, but that's because of the uncertainty as to what the phonon contribution is. And this is about as good as it's hard to do much better than this. Okay, and so that this 20% variation or so, that's kind of typical of what you would get. Anyway, so the entropy release is about 6 joules per mole per Kelvin and not 13 joules per mole per Kelvin. So it's a big, big missing entropy. Okay. And so that's one oddity, okay? And then the second oddity comes in the inelastic neutron scattering and the elastic neutron scattering. So this inelastic neutron scattering, when we first saw it, was more or less what we expected. We saw some gapped excitation that was present when we're below T star, and then the gap collapses as you go above T star. So, it could be, some sort of gap spin wave excitation spectrum, which is dissolving as you go through the phase transition, okay? So this is what the data looks like if you look at it all together. These are cuts through the data. So there's a bandwidth to the excitation spectrum that's about 6 MeV, and there's a spin gap of about 10 MeV. So this is all well and good. But if this were the same, and it kind of looks similar to the 5D3 case, okay, but I'm showing this on an intensity scale that shows the inelastic scattering, and it doesn't show the elastic scattering. So on the 5D3 case, there was a big Bragg peak right underneath it here. Okay, so that's kind of the thing that we expected to see. So let's look at that now on a different intensity scale, actually a logarithmic intensity scale, so that you can see the Bragg scattering. And the thing that I'd like you to note is that in this low Q regime here, there's actually no temperature dependence to it. Okay? So it looks like as you go through this magnetic ordering transition, there's no magnetic Bragg peaks, okay, that neutrons are seeing. And actually, we can we can be much more precise about this. We can do a different experiment, which is really optimized to measure these kind of weak magnetic Bragg peaks. This was done on D20 at the ILL. And we can look at temperature differences in this, this sequence of materials. So there's 3 different 5D2 systems. And you know, in this low Q regime, there's no temperature dependence to the scattering at all. And actually, we can model, you know, what would happen if we had, you know, Neel order, you know, with a moment of order 0.1 Bohr magnetons. So this is the simulated diffraction pattern. And so 0.1 Bohr magnetons is about our limit of visibility. Anything else, we would lose it in the noise. But this is telling us that there's no magnetic neutron scattering in any of these 3 cubic 5D2 double perovskites with an upper limit on the ordered moment of about 0.1 Bohr magneton. So I'm going to say there's no magnetic dipole order at T star. Okay. And right. So, and then this is just high resolution X-ray scattering that shows that these systems remain cubic down to low temperatures. And again, we tried to model, you know, potential monoclinic distortions, orthorhombic distortions, what have you. You know, those all split the cubic Bragg peaks. And the question is, you know, how much of a splitting has to be present before you would recognize it? And the answer is about 0.05%. Okay. So we can say that the system remains cubic to within about 0.05% in terms of differences in the lattice parameters. So the system is definitely cubic. There's no structural phase transition. There's no magnetic Bragg peaks, but there is an inelastic magnetic feature. Okay, and we don't have enough entropy. Okay, so this was really a you know, a quandary, and it remained a quandary actually until we ran into Aaron. Okay? And you see the recurring theme in this talk is that experimentalists are confused until, you know, a friendly theorist shows them the way, right? And that happens over and over again. Anyway, so these 2 papers were collaborations between ourselves and Aaron, his group rather. And so he postulated the following idea that he described actually on Monday, which is that we have this J equals 2 degree of freedom, but then you can think of it as behaving like you know, a d electron system, you know, in a cubic crystalline electric field environment. So this CEF prime is actually this general form of the residual, if you like, crystal field written in terms of these Stevens equivalent operators. And you know, depending on the sign of the B effective out front, it would split the 5 levels into, again, something that looks like, well, in this case, there's a non-Kramers doublet with some sort of a gap, and then a magnetic triplet on top. And if this is the relevant perturbation, then actually they could work out, you know, they could basically, you know, solve the problem, solve the eigenvalue problem, and determine the wave function in the non-Kramers doublet state. You can tune the gap between the non-Kramers doublet and the magnetic triplet. And you know, given that you know the wave functions now, at least within this model, you could then calculate that there is no expectation value for the JZ operator, so no magnetic elastic scattering is expected within the ground state. Okay? But there are dipole allowed transitions from the non-Kramers doublet to the magnetic triplet. Okay, so this is exactly consistent with what we see. No elastic magnetic Bragg scattering, but there is inelastic magnetic scattering, which is easily observed. Okay. So at any rate, right. So that then leaves the question of the μSR. Because the μSR is definitely seeing internal magnetic fields, and they're definitely turning on at T star, and that's why we originally thought that we had a Neel state. But as it turns out, if you go through the analysis, and this depends on knowing, you know, where the muon stopping site is. So we're going to put the muon stopping site at an oxygen position that's midway between an osmium site and a B site. At any rate, analysis of the MUSR data says that the local field is about 60 Gauss, which is a pretty low field for a magnetically dipole ordered system. But it's about the right order of magnitude if there are octopole moments associated with the osmium. Okay, and so you know, actually this could be estimated within the particular model of a ferro-octupolar ordered structure, and in that case, of course, octopoles do break time reversal symmetry, so there are magnetic fields, and but they're small, of course. And so actually what Aaron got was 30 Gauss compared to 60 Gauss, and I consider that a victory, right? That's close enough to be, for us to so now I think we've got a pretty consistent view of this. You know, what we're postulating is that there's a ferro-octupolar ordered state at T star in these systems. It accounts for the R log 2 of entropy instead of R log 5, a big difference. It accounts for the gapped magnetic inelastic scattering, the lack of magnetic Bragg scattering, the cubic symmetry down to low temperatures, and the time reversal symmetry breaking as seen by MUSR. Now, having told you all that, there's another very interesting theory, which actually was also Ginyad was talking about on Monday, which actually has quadrupolar order instead of octopolar order in it. And anyway, so mostly I'll refer you to this paper and to Ginyad. There he is, yeah. And I would just say that the wave functions that I showed you that Aaron had worked out, they carry both an octopolar moment and quadrupolar moment. So in principle, either of them could order. Now, if quadrupolar moments were to order, I would expect a structural distortion, but maybe it's too small to see. That's what they would argue. And you wouldn't necessarily see any magnetism, any magnetic fields in it, because it doesn't break time reversal symmetry, but there could be time reversal symmetry breaking associated with defects or associated with the muon itself. So that's the way that argument goes. Anyway, I'll refer you to Ginyad for any further details. So the last thing I want to talk about is actually unpublished work. So now I brought you ahead through 10 years, and this is where we are now. And actually, there's a lot of interest on the 5D1 system. And you know, for example, the next talk by Hirai-san is also focused on this, and there's another 2 or 3 talks after that. So there's going to be a lot on this. Anyway, so we also started working on this about the same time as Hirai-san started working on it. But actually, they published a very beautiful work before us, and we still haven't published our work. Anyway, so in this case, you've got a single electron that's in the quartet. So there's another J effective 3/2 degree of freedom. So there would be a 4-fold degeneracy associated with it. And actually, you know, this is the Japanese work that I was referring to, this very nice paper here. And what they see, so this is the heat capacity divided by T as a function of T. They clearly see 2 phase transitions. Okay, and so there's a high temperature phase transition at about 30 Kelvin, a low temperature phase transition at about 17 or 18 Kelvin, something like that. And at low temperatures, there's clearly a magnetization, which very quickly saturates in a magnetic field. Okay, and actually they recover about R log 4 when they look at the entropy. So this is interesting, and so this is, as I'll describe in a second, this is interpreted in terms of a quadrupolar transition, and this would be a magnetic dipole transition. And I don't mean to give your entire talk for you just before you do, but I'd also point out that, you know, and then at low temperatures with resonant X-ray scattering, it's an L3 edge actually for rhenium that they're looking at. They see the onset of this, of what looks like a magnetic Bragg peak. So, and in fact, they refined the data that they had in terms of this very unusual structure where you have basically ferromagnetic planes of rhenium atoms which are almost orthogonal to each other, and they have so the structure has a net ferromagnetic moment. But at any rate, it's an unusual magnetic structure for sure. And the only thing I'm gonna add to this story. So this is the a tentative phase diagram that was proposed. Has temperature versus the strength of the quadrupole interaction parameter, and you have this rather rich phase diagram. But they are imagining that barium to magnesium renate is coming down this line here. So first the quadrupoles order. There's a distortion of the structure, and then you get this unusual dipole ordered state at lower temperatures. So all of that is good. So at about the same time, we had synthesized the same materials. Actually, we also synthesized a couple of different ones. Yeah, I'm just about done, actually. Yeah, we'd synthesized a couple of different ones. And essentially, we reproduced all of the Japanese group's work, right? So we also saw two peaks in the heat capacity. So this is the magnetic heat capacity for the barium to magnesium renate. We also saw that at about 30 Kelvin, there's a splitting in these what are otherwise cubic Bragg peaks that are consistent with the same sort of distortion that had been observed previously. And we observed this in two different 5D1 systems. So this shows you some measure of the distortion off of cubic symmetry as you go down in temperature. And it starts at 33 Kelvin and then accelerates, as you go into, whatever that low temperature state is. So everything that we saw was fully consistent with the published data. Okay. We also saw at low temperatures that there's a magnetization that easily is saturated by a magnetic field. Okay. It saturates at about 0.25 or 0.3 Bohr magnetons for the renate, and this is a typo. Sorry, not for the renate. They're all renates. For the magnesium renate and then for the zinc renate, it's similar but smaller. Okay. And so these aren't very large moments, but they're still easy to observe by magnetization because of some net ferromagnetism. And then we went to look for basically this structure, right? This unusual structure with, but not with resonant X-ray scattering, but with powder neutron diffraction, because this should be observable. The ordered moments that were proposed here are 0.4 Bohr magnetons. And remember, with powder neutron diffraction, our lower limit is about 0.1 Bohr magnetons. So this is using the same, world-beating powder diffractometer at the ILL that I talked about before, D20. So actually, we looked at the difference between 1.5 Kelvin and 30 Kelvin, and we know where to look. We know which wave vector to look at, to check that we can see this ordered state with neutrons, and it's these positions here. And this is the simulated diffraction pattern with this structure and 0.4 Bohr magneton moments, ordered moments. And you can see that in this temperature subtracted data, there's nothing there. Okay? And in fact, the strength of the magnetic neutron scattering goes like the square of the ordered moment. So if you took this down from 0.4 Bohr magnetons to 0.1 Bohr magneton, this scattering would come down by about a factor of 16, and then you would lose it in the noise. But again, the neutron scattering is not seeing a dipole moment of anywhere near 0.4 Bohr magnetons with this sort of structure. And in fact, we're not really seeing anything other than the magnetization. So actually, this would be consistent so everything else is consistent. So one possibility is that the powder samples are different from the single crystal samples, but actually we reproduce pretty much everything except for the diffraction signal in the single crystals compared to the powders. But if you just look at our data on its own, it would be consistent with the low temperature state being a simple ferromagnetic state, in which case there are magnetic Bragg peaks present, but they overlap with the nuclear Bragg peaks, and they're impossible to separate from them. So there shouldn't be Bragg peaks if it was simple ferromagnet magnet, so everything sort of pointing in the same direction. There wouldn't be Bragg peaks here. There'd be Bragg peaks that would be sitting on top of these huge Bragg peaks, which you would not be able to see. Anyway, so this is unpublished work, and the only reason I'm bringing it up now is because probably half the people in the world that are interested in this problem are in the audience, and so I thought this is we've been quiet about this for a long period of time, in part because the published work has been so good and so complete. But at any rate, I thought this was a good time to bring this up. So with that, I must be out of time, and I'd just like to thank I'm not going to put up everybody's picture because it's just too much. So I'll put up the more photogenic collaborators, and then give you a list of the publications that ensued. So thanks very much.